and thank you for joining us today. My name is Armando Verdiel, Technical Development Supervisor with Lighting Design Lab. And today we're going to have a webinar on commercial heat pump water heating design, maintenance, and operations. Part one, that is part one of a 4-part series. It was a great deep dive to all ins and outs of commercial water heaters, presented alongside Colin Grist from Ecotope and moderated by Trevor Davis from DNR Learn. Just very excited to start the series with you guys. Just very quick rules of engagement if you haven't seen our webinars before, but on the bottom right-hand side of your GoToWebinar dashboard, you'll see the chat window. Feel free to engage with us using the chat. It'll pop up questions if you've got comments. Trevor and Colin will also have a Slido application for additional engagement. Encourage you guys to tune in and engage. The more you put into it, the more we'll get out. Without further ado, I'll give it up to Trevor and Colin.
Thanks so much, Armando, and thank you all for joining us today. As Armando said, my name is Trevor Davis. I'll be moderating for you today, and our trainer today is Colin Grist. Just reiterating too, please use the questions and the questions feature, and you can just pop it out and have it there as another window. I'll be keeping an eye on that. So as Colin progresses through the presentation, I'll be keeping an eye on if questions do come in, I will have them stop and we can address those, and would love for you guys to participate as much as you would like to, and if you have any questions throughout, please don't hesitate. So with that, I'll hand it off to Colin. Thanks all for joining us.
Great, thanks Trevor. Welcome everyone. We have a great 4-part series here on commercial heat pump water heating systems. We're looking at design, maintenance, and operations of these systems. My name's Colin Grist. I've worked at Ecotope for 8 years now in the commercial building world, and I have specialized in heat pump water heating for the past few years, really focusing on how to get these amazing, super energy efficient systems into the commercial buildings that we're working on, commercial, residential, to office, to retail and restaurant. These systems are great for numerous building types, but today we are fairly focused on commercial multifamily. As we're in Seattle, this is hosted by the Seattle Lighting Design Lab, and we're focused on some of the new code requirements in the Seattle area that's requiring commercial heat pump water heating systems for R1 and R2 occupancies. So that's residential and hotel motel. And residential is greater than a few or 4 units, I believe. So like I said, we have a 4-part series here. Today, we are really looking at commercial heat pump water heating systems through the lens of the developer, or really early on in the project, early SD schematic design phases. What the system is, what it can do for the building as far as energy savings, and how it can provide hot water for the tenants of the building. Session 2 is really focused on some of the key design considerations. So this is looking through the designer, the plumbing designer, or the engineer on the project, and understanding what are some of the key design considerations that they need to be aware of and attentive to make sure these systems get installed effectively and result in very efficient operation in the buildings. And then session 3 and session 4 are hosted by my coworker, Evan Green, who's super great. He also has a wide breadth of knowledge on commercial heat pump water heating systems and has worked for commercial heat pump water heater manufacturers in the past. So really always a great pleasure to hear him speak. And in session 3, he's really focused on taking the design that a plumbing designer drew up or an engineer drew up and implementing that into the actual building. So looking at the submittal process, working with manufacturers to make sure that correct equipment is specified and delivered to the site. It's a really great session on basically taking that design and actually moving it forward and start looking at purchasing and getting these systems installed in buildings. And then session 4 is all about maintaining an operation. Both session 3 and session 4 have some on commissioning, and so that's always a great thing to stick around for, as it's super critical to make sure these systems are commissioned and set up appropriately. And so session 4 is definitely looking through the lens of that commissioning person, as well as the building maintenance person, to ensure that these systems have been installed correctly and will be operating efficiently for a long time, right? We want to spend our money and make sure it's set up correctly and will be working for a while. So really great couple sessions later on. Session 1 and session 2, I've talked a lot about heat pump water heating systems for the lighting design lab, so some of this may be a little repetitive for folks who've joined us for earlier webinars in the commercial heat pump water heater series, but still great information here. And if you have any questions, we are more than happy to cover them throughout this presentation, and Trevor's always doing a great job of that. So this is our plan for today and for the next few weeks, but I encourage your questions, as we really want to tailor this webinar and series to you, our audience. And if we can help answer some of the questions that are more prominent or you consider more important, we would love to help in that process. So session 1, we are getting started on why would I want a commercial heat pump water heating system in my building? Right, that's the key question we're trying to answer today, is what the system is and why am I interested in it. And before we get started on diving into this presentation, we want to get a little interaction from you, understand who's in our audience today and what you work on, what your experience with heat pump water heating systems are, and if you have any questions, this is a great time to add them. And so we have a Slido, which is a free web-based tool. They don't log any of your personal information. There's no sign up required. All you have to do is navigate to slido.com and enter that event code you see there, design1. So I'll give us all a little bit of time to do this right now, but this is our introductory survey. We're just looking to understand who is in our audience and if you have any questions that we can try to address throughout this presentation. There's also a QR code in the upper left-hand corner here. So if you have your smartphone, you can snap a picture of that and it should take you right to this introductory survey. And I'll give us all a few minutes to navigate there. It looks like we got close to 20 people today. So that's a great size class. Always great to have questions when we have a smaller group like it is today, as we can really tailor this to our audience.
Yeah, we just say too for the Slidos, when you have the Slido open, you can just leave it open on either your phone or another tab, and as we progress through, there's a few other Slidos throughout the presentation, so it'll automatically update, so you don't have to navigate to it next time. So it should make it a little easier for you. And if you have any questions or issues getting on, just shoot me a message and I'll assist.
Great. Well, it looks like some of us found it out there. And what professions do we have joining us today? We have an engineer, welcome, utility personnel, project manager, energy analyst, all fantastic that you are all joining us today. We will once again be focused really today on looking at this through the early design phase lens, kind of the developer's lens, why they might want this system in, but also through the engineering lens, why you might be encouraging a developer to install one of these systems, or as far as the energy analyst, right? We want to set these buildings up to be really high performing buildings. And so it's great that I can hopefully share some knowledge on why you're going to be interested in one of these commercial heat pump water heating systems. And a utility energy efficiency person, program manager. What is your experience with commercial heat pump water heating systems? Novice, 100% novice. Wow, awesome. Oh, there's some dabblers in the group. Great. I think most of us out there in the world are pretty novice to these commercial heat pump water heating systems, especially in the United States. European countries, some countries in Asia are much more advanced on the commercial heat pump water heating systems, and they have a much larger market with these systems serving the domestic hot water loads in those nations. So in the US, we're a little bit behind, and that means some of us are maybe in the novice category, but I hope we can bring you all up to at least the dabbler and really share some of our experience that we've learned at Ecotope working with these systems for the past 10 plus years, so that we can all be moving quickly in the right direction, because the name of the game is energy savings here. What questions do you bring with us today? We'll try to go through these, but let's look at them right now. What are the best efficient systems and how that is deemed? Yes, so the advanced water heating spec 8.0 is a new, or 8.0 is the new revision of that specification, and that's authored by NIA. And that is looking at the system coefficient of performance, or the system efficiency. And so we will touch on that in the webinar session 2, as well as later in session 3. And so we'll break down how you really achieve that most efficient system, and how programs like the NIA Advanced Water Heating Spec is rating that efficiency. And they're looking at it as system approach. So any backup equipment in there would be counted in that overall efficiency. And we'll get into those details in later sessions. So I hope you join us for those. Understanding the basics, that's exactly what we're trying to cover today. So please stay tuned in, and we'll go through those basics. Cost differentials of commercial heat pump water heating systems, energy impacts of commercial heat pump water heating systems. So we're definitely going to go over energy impacts today. We are going to get into cost as it relates to sizing of these systems in the next session, which is, I believe, next week on Tuesday morning. So please join us for that. But we can make these systems very cost effective, and that might mean approaching the sizing of the commercial heat pump water heating system different than we've approached sizing of a traditional gas or electric resistance system. So great information there in our session 2. Getting started, happy to learn technical concepts and design considerations. Yes, so if you're an engineer and you're just getting started, this is a great session, but please join us for the remaining 4 sessions, as I think there's a plethora of great design considerations and technical concepts that we'll happily share with you. Then what is COP? Well, it's not a COP, it is the coefficient of performance. So it's looking at how much useful energy we're getting out of the system compared to how much energy we're putting into the system. So in electric resistance, we're going to put in electrical energy and we're going to get out useful water heating energy, and that might be a 0.98 COP or 98% efficient. A heat pump water heater moves heat, it doesn't make heat, and we'll get into this later. And so it operates at a much higher efficiency because it is more efficient to move heat than it is to make that heat. And we'll get into those details later, but that's going to be operating at a COP closer to 3.0 or 300% efficient, which is really why a lot of the codes, the jurisdictions, and there's a big national effort to get more of these really high efficient systems into the buildings that we're designing and constructing today. So great question so far. Keep adding them to the chat. Trevor always does a fantastic job of moderating those questions and asking the ones that are tied into what we're talking about at the time. So case studies, everyone loves to see one of these systems in person, and unfortunately COVID is still, with us and changing how we interact in the world. And so a lot of us don't have the opportunity to maybe go into some of these buildings, or it's more challenging to get there. And so we'll walk you through a case study here on Hope Workstation, which is a newly constructed multifamily building in Everett. It's 4 stories tall, 3 stories of residence, over 1 story of commercial, retail, and support spaces for those residential apartments. And believe it or not, Hope Workstation has a commercial heat pump water heating system. However, it's using a residential heat pump water heating product known as the Sandin heat pump water heater, or Sandco 2. There's been a recent rebranding. And so that heat pump water heater is providing hot water to the tenants of this building, and it's working really efficiently and really reliably to deliver that hot water. But we didn't do probably the most typical design solution here, as we were working with a smaller residential heat pump water heater product that was sized to serve about 4 to 6 people. Right, we have a larger building here. It's about 100 units, and so we were looking at a larger commercial load. We decided as the design team to design around the Sandin heat pump water heating technology, as it's a CO2 based refrigerant, and all that means is it can work in cool ambient air temperatures. So it can work in Washington State even when there's snow on these mountains and when it's 25 degrees outside, right? These are really highly efficient systems that use CO2 as the refrigerant, and those allow us to move heat into water even when it's very cold outside, and it does get cold here in Seattle occasionally. So what this system looks like, it does look a little bit different than maybe your typical water heating system where there's 1 or 2 water heaters in the basement and that's serving the entire building. Here, the design team decided to break this building apart, and we're serving units vertically. So like I mentioned, there's 3 stories of residence, and this heat pump water heater here is serving vertically 3 units, which is about 6 people, 4 to 6 people in total, depending on if those are 1 bedrooms or 2 bedrooms or studios. And we repeated that across the entire building, putting numerous of these heat pump water heaters on the rooftop and serving in vertical piping sections. And so we also located a hot water storage tank, and this is 1 level below. So that's right on the 4th floor there. That's accessed through a maintenance closet. And so that allows us to have a little bit of a thermal battery so that we can store the water heat, or the hot water in that tank, and serve it to those tenants and meet that building load. So looking at this with a few more details, like I said, this is for new construction, and there's 13 of these Sandin single pass heat pump water heaters, and we'll get into what a single pass heat pump water heater is a little bit later today. And these are connected to mostly 120 gallon storage tanks, but there are 2 84 gallon storage tanks. And so essentially you have 1 of these Sandin heat pumps connected to 1 storage tank on the level below. And then because hot water recirculation, or temperature maintenance, as we also call it, is a challenge for this specific heat pump technology, we decided to implement heat trace on the piping, hot water piping. And so our temperature maintenance system, our hot water recirculation system, keeps that water in the piping hot because it's either circulating it or it's maintaining that temperature with an electrical element, like in this case. And that was definitely something that we designed in purposefully. And unfortunately, the electric resistance heat trace is operating more than we intended it to, or modeled it to, which is creating a degradation on that system COP, or the entire efficiency of the system. But it does allow the Sandin heat pump water heater to operate in a really efficient state, and also very, very reliably. And so our end goal here is to deliver hot water to the apartment buildings or the tenants of the building, and then make it as efficient as possible. If we're not delivering hot water, or there's issues, right, the efficiency is less important, because we must serve that requirement first for hot water. And these Sandin heat pump water heaters are located on the rooftop. And like I said, they use CO2. We'll get into refrigerants later on in session 2, but that CO2 refrigerant allows us to operate those heat pumps even when it's really cold outside, where other types of refrigerants may be limited to, let's say, 40 degrees Fahrenheit as the coldest temperature they could operate in. And then a little bit of some metrics on the energy use there for any energy models in the group, but that's about it's cutting the energy about 2.5 or by almost a third of the energy. So sorry, excuse me. So we cut the energy, but by about a factor of 3. We're using about a third of the energy of a typical water heating system for this high efficient Sandin system. So any other key takeaways? One key takeaway I had with the design team that worked on this project was these clustered systems using smaller residential equipment can be very economical, right? This is for a low income, primarily formerly homeless population the building HopeWorks is serving. And so the project, like all projects, was constrained financially, but maybe more so in this application. And we really demonstrated that these smaller residential heat pump water heating equipment can be used in a commercial application. We just have to approach that design a little bit differently than maybe we have in the past. And this can be a very economical installation. So that's one of my key takeaways. And if others have them or anything else you're interested in exploring in the case study, we got our Slido friend here again, and I'd love to hear either some of your key takeaways or what you're interested in learning more about with this case study we just went through.
Colin, was there any sort of specific details you had to keep in mind, like knowing the sort of population that was going to be moving into those buildings, and maybe how they would be using the building differently than just like a regular sort of like maybe commercial space?
Yeah, so we will definitely talk about sizing and sizing for the hot water load. But like Trevor mentioned, if we all use hot water in the morning in more of our typical market rate apartment example, and then there's a lesser peak in the evening when we're cooking and cleaning, that's one load profile and we have to size for that. If we're in an office building, there might not be that high demand in the morning because in office buildings, we're typically not taking our shower, but we still might have water use throughout the day. And maybe we don't have that evening peak too. However, in a commercial kitchen or an assisted living facility, that water use profile will change a little bit. And so we have to always be sizing for that. And we have some tools that we've developed here at Ecotope to help us all understand that sizing and some of the trade-offs, excuse me, so that we can appropriately size these systems, because that's how we really save money with the first cost is appropriately sizing. What are the environmental, so we got some questions here or things we're interested in learning more about. What are the environmental effects of using CO2 as a refrigerant as opposed to R134A or other typical refrigerants? This is a fantastic question. We're going to cover global warming potential and refrigerant selection in session 2, so please join for that. But the overall summary is CO2 refrigerant is the basis of the scale, so it has a global warming potential of 1. R134A and 410A, the more typical refrigerants we've used in the past in a lot of mechanical systems, have a global warming potential in the thousands to 1,000, I think 800-ish to 2,000 plus. So CO2 is a much more environmentally friendly refrigerant as opposed to R134A, which I think is what that was supposed to indicate there. Maintenance issues, yes, this is something that we thought about a lot, is maintenance issues with cluster equipment and equipment failure. Luckily, or one of the design solutions we looked at was, this is a residential product that's essentially available off the shelf. So it's a commodity product, and we can get a very quick, we can get a new one fairly quickly, or the project team could. And so if something did fail, there's replacements there. If we're looking at a much more custom system that may be using a custom heat pump water heater that has a longer manufacturing lead time, a clustered system like this might not be the approach to take. There are some additional maintenance issues or maintenance points, right? Now we have 13 heat pump water heaters spread across the rooftop instead of maybe 1 or 2 large heat pump water heaters in a basement or garage or some kind of mechanical space on the roof. And so there's more maintenance points for those personnel to attend to. But the first cost savings were substantial enough, as well as how the system was laid out on the rooftop, really tried to minimize those maintenance procedures and tasks and make it very easy for them to be done. One of the things we have with maintaining heat pumps is cleaning air filters. And so we wanted that heat pump on the roof to be easily accessible, not on a penthouse roof, so that the air filters could be easily cleaned on a quarterly basis by the maintenance personnel. And then sizing, yeah, we're definitely going to get into sizing in session 2, but we can essentially trade off how much heat capacity the heat pump has with how much storage we're providing for the system. So that storage tank is our thermal battery. We can think of it just as an electrical battery. If we make it bigger, we can essentially serve more of the load from that battery alone. Our heat pump, we can think of as our solar panels. And so we can have a small trickle charge, charging that battery throughout the day, and that works as long as we don't get 2 peak loads right next to each other. So we definitely go into more about sizing in session 2, so please join us for that. Any residents' complaints about water temperature is not hot enough? Not in this system or in any heat pump water heating systems, as long as you're implementing it right and operating within those the heat pump water heater boundaries, the equipment boundaries and limitations. The Sandin actually makes 150-degree water, and that is stored in the storage tank, which allows us to use that thermal battery more effectively because we have more thermal energy in that tank. But it does mean that we need to mix that water down. So we take the cold water and that heated water at 150, and mix those together to always target 120-degree Fahrenheit out to those tenants. And that's one of our common design solutions using heat pump water heater technology.
Hey, Colin, had a question, didn't make it into the Slido, but came in from another route. If you can comment a little bit on it, just open question. Hey, any information on reliability yet on heat pump water heaters?
Yeah, speak with your manufacturer. There's numerous manufacturers out there right now. Sandin is one of them. They tend to be fairly reliable products. There's been some issues early on with some of their components, but manufacturers are always trying to improve their products. So please, speak with your manufacturer's representatives or whoever you can get a hold of. But in general, commercial heat pump water heating systems are very reliable, just like the residential heat pump water heater products. I have a residential heat pump water heater in my basement here, and it has been working fantastically for the past 5 or 6 years, and has saved me an enormous amount of energy and dollars. I mean, put money in my bank account. So they are fairly reliable. It's really the misapplication of a heat pump water heater that causes reliability issues is what I would say. It's not the actual product itself, it's misapplying that product. So we're going to cover next why choose a commercial heat pump water heating system, and really we're talking about energy savings here. but there's also other policies, both global, federal, and state, that are driving these changes. Those federal policies or state policies are typically impacting the codes and standards that the engineers and designers in this group need to design around. But there are still incentives and rebates available, and Seattle City Light offers some incentives for certain types of heat pump water heating systems using certain technologies. So even today, where a lot of these are code required, there are still incentives and rebates available. So a great opportunity to capture some of those, as I doubt they'll be here forever. And then we can lower our operating costs substantially with a heat pump water heating system. If we size and install these right, we're typically well under that 10-year payback. So great reasons to really recoup, or a great way to really recoup your first cost investments in a reasonable amount of time. And then energy efficiency measures. This is one way to really drive down the annual energy use in our buildings. With a commercial heat pump water heating system, it is one of the low-hanging pieces of fruit. You can easily grab it and achieve it, and it always typically is resulting in a really energy efficient system and a lot of energy savings. And then societal changes, right? Gas has kind of had its heyday and is moving out. There's reasons and places to use gas, but in our built environment, we're seeing now that gas ranges in our kitchens are creating higher rates of asthma in our children and our young populations. And there's other reasons as far as global warming, climate change, that we're moving away from these gas systems. We're also seeing the skyrocketing prices of either natural gas or some of these other fossil gases. And so society is looking for cleaner solutions, healthier solutions, and more cost-effective solutions. And heat pumps are definitely all three of those. But really, we are focused on multifamily building a little bit more specifically today, because in the Seattle Energy Code, we are now required to serve our commercial multifamily buildings with a commercial heat pump water heating system. And one of the reasons why the code is really driving this first for this building type, or this occupancy type, is really looking at the energy savings possible here. And so on the left-hand side of the screen, we have our baseline multifamily building. And this is all the energy that's going into that building over the course of a year. So we can see that about 25% of it is associated with domestic hot water. Another 25% is our apartment plugs and lights. And then there's, some HVAC, common plugs and lights, and common HVAC. Those are garage exhaust fan systems, our quarter ventilation systems, quarter heating, cooling, and so forth. And if we're focused on this domestic hot water load and we apply a heat pump water heater to that, we end up saving about 17% of the annual energy. So 17% of the total building energy can be saved just with this one technology, often replacing a more outdated gas water heater in the basement, or if it's a new construction, a more efficient solution being installed there than a gas or electric system. And so we can see that the domestic hot water primary heating load, which was about 15% of the annual energy, was cut down to 5%. And the domestic hot water temperature maintenance load was cut from about 10% of the annual energy to 3%. And one of the things that I found really interesting when I was first starting on the heat pump water heater, kind of starting in that world, is how big this temperature maintenance piece of the pie is. This means we're wasting 10% of our energy, because this is keeping the water hot in that distribution piping, and all that heat is being lost to the building environment. In the winter, that heat being lost to the building is probably pretty good because it's heating that building a little bit, But in the summer, as we get more cooling needs in Seattle, this is just creating more of a problem for us. And so there's a substantial amount of energy wasted, right, in keeping that water hot in that distribution piping. So we'll go over some techniques to really reduce that load, as we'll discuss why it's so important and so influential with our heat pump water heating system. And that really gets into some of the design considerations for these technologies. But all in all, what I want to drive home here is that a commercial heat pump water heating system in a multifamily building will typically reduce the energy usage by a factor of 3, saving you about 70% of the total building energy use. So this is a great way to achieve LEED Platinum or some other high level of energy efficiency certification. Numerous programs out there, but LEED is probably the most common one we're all familiar with. And then we're doing it in Seattle, or we're really focused on Seattle on R1 and R2 occupancies, as the new code is requiring air source heat pump water heaters, not fossil fuel or electric resistance, for R1 and R2 occupancies with central commercial service water heating systems. So what this means is any buildings greater than 3 stories, residential buildings greater than 3 stories, or any hotels or motels are now required to implement a air source heat pump water heating system. And it's January 25th, so that's been the case for the past 25 days of this year. And those codes are pushing for that adoption because, like I showed in the pie chart example, is there's an enormous amount of energy savings potential here. And if we think about this globally or in the United States, is every year we use more energy, and we have to either be making new power plants, installing new solar systems, wind turbines on our buildings or in our built environment, or we can be saving energy, reducing the energy that we use. And so we need to start thinking about energy efficiency as a source of energy generation. Because if we save energy, that means we don't have to be generating that energy with typically a new energy generation source, hopefully a clean and efficient one, but that might not always be the case. So this is Sunset Electric's apartment building. This is right in Capitol Hill. I think it's probably been open for about 8 to 10 years now. The Seattle East Precinct is right there. And this building has a commercial heat pump water heating system in it. It's using older Colmac R134A heat pump water heaters, and they're in a parking garage. And we'll discuss later on in session 2 why we installed them in a parking garage. But what happened here is the Seattle baseline, which is this pie chart here, the annual energy usage was about 39, or an EUI of 39. And so that's looking at all the energy going into the building over the square footage of that building. And that was the predicted baseline. And so we installed a heat pump water heating system and other energy efficiency measures in this building and reduced that EUI to 22.7. And that's actual measured performance. So we were able to dramatically reduce the energy usage there associated with heating that heating water for domestic applications. And that project used a R134A large commercial heat pump water heater technology. And this one I'm showing here, which achieved about the same amount of energy savings, used 4 Sandin or Sandco 2 heat pump water heaters. And this is an existing building that was built in probably the 60s. And it had an existing electric resistance water heating system in it. And we retrofitted this building to a heat pump water heating system using those really highly efficient CO2 heat pumps that are located outside, and they're right over here just out of the frame of this picture, unfortunately. But that resulted in a massive amount of energy savings for this project, and that equated to about $6,400 per year of energy savings here. So another really great example of a retrofit case study with a heat pump water heating system.
Colin, we did have a question just sort of on talking about the building code. Someone had asked, does the building code affect buildings that are started construction before 2022, or is it just anything that started in the past 3 weeks?
That's a great question. It matters what code you're vested under. So that's going to depend on when you applied for your permit. It was probably earlier than a few weeks ago, so you're likely under an earlier revision of the Seattle Energy Code, which the Energy Code, not the building code, is regulating or requiring heat pump water heaters for commercial multifamily.
Got it. Good distinction. Thanks.
Great question there, though. So, I mean, what's your motivation out there for implementing a commercial heat pump water heating system? We have another Slido here. Are you motivated by the energy savings, the financial savings, the payback, the lower greenhouse gas emissions? Do you want hot water and you want it most efficiently? What's your motivation out there? Code compliance is another one we often hear. EUI reductions, absolutely. It's a fantastic way to really drive that EUI down, or energy use intensity, the amount of energy we use over a year divided by the square footage of our building conditioned area. Reduce gas on building stock, or GAG. Not sure. Oh, global house or greenhouse gas emissions, that makes more sense. Reduce greenhouse gas emissions on building stock, yes. Electrification, yeah, we have a very clean source of energy, electrical energy here in Seattle. It's not the case everywhere, but it primarily comes from the Bonneville dams or the Bonneville Power Administration, the dams on the Columbia, and that is a super fairly green electrical energy source, as we've already constructed those dams, and there's typically enough energy on an annual basis coming out of them. Energy reduction, yep, excellent way to reduce your energy in the building. Energy savings, lower greenhouse gas emissions, fantastic. Glad you're all thinking along those lines, and future-proofing your buildings. So next, we're going to cover what is a commercial heat pump water heating system. I showed you a few case studies, the HopeWorks project, and then Sunset Electric, as well as two kind of light case studies on Sunset Electric and Elizabeth James House. But we're going to dive into really what a commercial heat pump water heating system is and how it can be configured and look. We might see a little bit different between one system and the other, depending on what building it is serving. But the first thing I want to cover is there's two typical product types. We have the unitary or the integrated heat pump water heater. Everything in this regard is packaged. The compressor, the heat pump, the tank, the controls, they're all in a single package, comes from a manufacturer, delivered on site, and can be installed. These are more typically available in residential product sizes. So usually that means less than 1 ton of heat capacity or 12,000 BTUs per hour. But there are some available in a more light commercial size or for small commercial buildings, and I would push you towards A.O. Smith there, or I'd recommend that product as is. It's one of the more small unitary integrated heat pump water heaters, but is sized for a light commercial application, perfect for a restaurant environment. And then the other type, besides our unitary, is the split system. And all this means is the compressor, the heat pump, is split from the tank. And this allows some design flexibility, because now this compressor, this heat pump, it needs a source of air. So we can put this outside and we can put a tank in an enclosed closet. And so we don't have to ventilate that significantly. if we were to put this product in a closet, we need to vent that closet with large air terminals and openings because heat pumps are extracting heat from the air, so they have a large air source requirement. So the split system allows for some design flexibility, which is great for us designers and engineers out there. It adds a little bit of complexity as it's not all in one packaged, but these are typically provided in larger commercially sized products, but there are a few available in the smaller residential sizes, like the Sandin here is a smaller residential product. But in general, we either have the unitary or the split system, and what that means is everything's packaged together in our unitary case, and split system, it's a few of the components are split apart. We're still going to have a control system built into this heat pump water heater, but it's not all packaged in one clean, convenient package for us. And there's a variety of ways that these heat pump water heating systems are delivered to the market. And I am a woodworker when I'm not being an engineer. And so I'll use my woodworking example here, but the custom engineered system is going to dun lumber, picking out your rough sawn lumber, taking it back, jointing it, put a flat edge on it, ripping it on your table saw, planing it down, and making a beautiful piece of custom furniture. That works for some of us that have those skills and have that know-how and know what resources we need to pull from to make that happen. But it might be, one of the more expensive ways to get these systems delivered into our market. And so what the custom engineered system really looks like in our heat pump water heating world is all the pieces are separate and typically can come from multiple distributors or manufacturers. So you might buy a Colmac heat pump water heater, and you might buy a Bradford White storage tank and connect those two together. Colmac will provide you with the thermostat for control, and you have to put that in the storage tank. And then you might want some backup system. So you might be using a big water heater or something to provide backup or redundancy in your system. This works. You can have a very efficient and very effective system with this type of design approach if you do it correctly and have those skills to make sure it's implemented. There are other ways to deliver these to the market, and this is more of the IKEA approach to my woodworking example with the specified built-up system. So in this case, all the pieces might be separate, or some of them might be separate, but they're typically coming from a single distributor or manufacturer, and they're giving you a nice set of plans to show you how you connect all these up so that you're operating their heat pump water heater product in a very reliable and efficient operating state, right? If we're operating this unit outside its boundaries that the manufacturer defines, then we're going to have issues. And so this specified built-up system is really taking that guidance from the distributor and manufacturer to make sure that these are implemented effectively and efficiently all across the board. So the specified built-up system is a great way for these products to be delivered to the market. And so maybe plumbing engineer or plumbing designers might be looking more towards this route for a lot of our market rate buildings that we're building. And maybe in our really high efficient or project with a lot of energy efficiency goals and some interesting project constraints, we might be looking more at that custom engineered system. And then the last way that things are typically delivered to the market is, it's great to see this is happening, is a package or skid system where instead of you building that chair out of rough sawn lumber or buying that chair at IKEA and putting it together with your Allen wrench, you're buying that chair from a furniture sales place. And that can be delivered to the project and installed on the roof. Typically it's a single package. Sometimes the skids are split out into two packages just for, construction and sizing reasons. But typically it's a single package, and we're connecting a hot water pipe, a cold water pipe, a hot water return or circulation pipe, and then electrical and communications to that device. And that system would be off and running, providing hot water to the building after being commissioned, of course. So really great to see that manufacturers have been, operating in this very custom world, but they're pushing their products to this more specified built-up system, which takes some of the burden off of us, the designers in the group, and then also pushing it towards more of the package system, which is definitely going to reduce cost and also increase the reliability of those systems delivered to the market. But I want to make sure that we all understand kind of what a commercial heat pump water heating system is and its typical components. And so I have a residential heat pump water heater integrated unit up on the screen here today. And I'll try to do a little comparison here to show you that the commercial system isn't always that much different. It has the same fundamental components. They're just spread across a room rather than in one convenient package solution. So the first component we have is the heat pump. And on our integrated unit, it might just be that heat pump on top of a storage tank like I'm showing here. But in our commercial, larger built-up systems, this is from Jackson Apartments, a new construction building in Seattle, Washington. We have 2 Colmac heat pump water heaters that are operating in parallel to serve the load. We also have some kind of backup system here at Jackson Apartments with a large electric resistance storage tank. And so in the integrated example, there might be a electrical element in that tank that can provide heat to the system if the heat pump ever has issues or is it's too cold outside in some scenarios. And then we have some way to store that water in our residential integrated unit, right? That's the tank directly below the heat pump typically. And in our commercial system that's built up, custom engineered, we might have 3 tanks in series to get that larger water volume. And then controls, we have some way to initiate the heating cycle here. And with our larger commercial systems, we also have that, but that might be a control panel on a wall of the room. So once again, there's a lot of similarities between these, the residential integrated heat pump water heater and our larger commercial built up systems. And they typically come down to those 4 components: the heat pump, some kind of backup occasionally, storage tank, and some control system. And we also have numerous products available. So I touched on this a little bit. There's 2 integrated or unitary heat pump water heater products here. There's many more than I'm showing, but I just picked 2 from each category for this example. And these are smaller residential size product, and this is a light commercial heat pump water heater by A.O. Smith. These are using R134A refrigerant, which struggles at cool temperatures, and that's below 40 degrees Fahrenheit. So you might want backup if you're installing these outside, and if you're installing them outside in Seattle, that's gonna degrade your overall system performance quite substantially because that backup system will engage. So you might be looking at a split system single pass CO2 heat pump water heater, which is not as challenged by the ambient air temperature, right? We can operate these down below freezing, still provide heat to the system, which is pretty amazing. But unfortunately, there's really only 2 manufacturers out there. There's Sanco 2, and this is the smaller residential size product, and Mitsubishi, which we're all familiar with. They make a lot of mechanical equipment out there, and they have a 10-ton heat pump water heater. Colmac and Nile are also using R134A. These are split system heat pump water heaters and can be set up in single or multi-pass, which we'll get into shortly. But they are, because they're using R134A, they're challenged when the air conditions get below about 40 degrees Fahrenheit. So lots of products out there. There's more than I'm showing on the screen here. There's more split systems commercially available. So please go beyond these two manufacturers if you want to do some searching. But there are some great options here. And really, it's important that the design team matches the project requirements with the equipment selection. We can put a 10-ton Colmac to serve a 4-unit multifamily building, but that is not going to be cost effective, and there might be some issues with the sizing there, as it can be oversized in that application. And so here's a few more examples, right? The large commercial system, we just looked at this. This is the Jackson Apartments building. We're using 2 of those R134A heat pumps. We put them in a parking garage to get some buffering on the ambient air temperature, because parking garages in Seattle, even on the coldest day of the year, if they're enclosed and underground, the low corners of them typically stay right around ground temperature, or around 40 to 50 degrees. So we can operate these heat pumps year round if we put them in an enclosed but ventilated parking garage and put them low down. So there's a lot of that great earth contact, and get some essentially geothermal effect out of this system. But we can also have smaller commercial systems using these integrated products, and we can combine 2 of them together, or maybe a storage tank to extend that thermal battery and serve a bigger load. We can locate these in a closet, but we need to duct them if they're in a closet. So there's some considerations there. And also we can look at multiple commercial systems for a single building, serving vertical, like in this HopeWorks example. So there's Evan Green there doing some commissioning and startup for this project here. He'll be speaking in session 3 and 4. So there's multiple sizes, types, and configurations, and we'll get into those details and some of the design solutions or design considerations you need to be making in session 2. But this is really just to highlight that there's a commercial heat pump water heating system may look pretty different from one building to another. So if we have a small commercial building, maybe 2 to 6 residential units, a residential or a unitary heat pump water heater might be the most economic solution, and it's still going to achieve really a high level of energy savings. And so we can essentially pipe 2 of these residential heat pump water heating products together, and then out to a thermostatic mixing valve and out to the building, and take the hot water circulation back to those 2 primary tanks. This can be, a very robust and efficient design solution for smaller buildings, and can be a very economical approach to get these heat pumps installed. The integrated residential products also work really well for commercial kitchen environments. We typically always have a cooling requirement in those commercial kitchens, and a heat pump is taking heat out of the air, putting that heat into water, and discharging cool air. So we can essentially discharge that cool air into the kitchen, get some free cooling out of that, that process, and be making hot water with a really highly efficient heat pump water heater all at the same time. So a great opportunity to kind of double dip on your energy savings, and get some cost effectiveness if you can downsize your cooling system serving that kitchen. This works really well too, because when the kitchen is on and working, it typically has a cooling load, and when the kitchen is on and working, it typically has a hot water load. And so it's necessary to not only match those loads together it's necessary to match those loads together at the same time to really get that savings effect that I'm talking about. But if we have a larger building, this is a building, boutique apartments in the Yesler redevelopment area. There's the Seahawks and the Mariners stadiums back there. We might be looking at a larger commercial equipment. We're not going to put 30 integrated products to serve this building. We might, but probably won't. So we might be looking at a more engineered system to provide water heating to these 200 units. And we'll get into dedicated systems and why you might want to split out the hot water circulation heating task later on in session 2. But in this example, we have 2 Colmac heat pump water heaters connected to a group of storage tanks. I'm only showing one in this conceptual diagram. And those work in parallel with a heat pump water heater and a temperature maintenance tank. So this heat pump water heater is keeping the water hot in the distribution piping. That's its #1 goal. These heat pump water heaters are heating cold water that comes in from the city and storing it to be used by the occupants. And it may be necessary to split out those two use types or those 2 loads. And the Seattle Energy Code actually requires that in some situations, which we'll get into later. And then also, multiple commercial systems, driving this one home. Here's HopeWorks again, and we can see our heat pumps spread across the roof top, and those are serving this building vertically. This can significantly reduce the cost. Someone noted there's more maintenance points or maintenance considerations. Yes, so you just want to make sure these are all easily accessible. We have maintenance requirements cleaning the solar panels. We have maintenance requirements making sure the grease of the grease exhaust fan is properly attended to and cleaned out periodically, and other requirements on air filters. So putting more mechanical plumbing equipment up here is adding maintenance points, but this is already an area where the building maintenance personnel will be attentive to in their daily or weekly routines. So we'll pause for questions here, and we're about at the hour mark. So let's take a 5-minute break, come back at 11:07, and we can address any questions that came in during that break. So please feel free to add those questions to the chat in the next 5 minutes or so, and we'll try to address them before we move on to the components, the 4 components of a commercial heat pump water heating system. We'll give everyone a little bit more time here to get back to their desk. Hopefully Trevor's got some questions prepped for us. All right. Welcome back, everyone. Hopefully you had some time to stretch, get a fresh cup of tea, coffee. And Trevor, do we have any questions?
Yeah, we did have one coming here from Garrett, so thanks, Garrett, for dropping in there. It's a general question going back to HopeWorks, and sorry if you missed it, but how long have the heat pump water heaters been running, and is this their first winter?
So at HopeWorks, this would be their first winter. We have used that same product and technology at Elizabeth James, which has been operating for probably 2 or 3 winter seasons now. And both have been successful. I was actually not very involved on the design team of HopeWorks, so I don't really know if there's been any recent issues, but I haven't heard of any, and I typically would.
Got it.
So it can be a very reliable system, and it's very surprising but amazing that we can pull heat from the air even when it's
like that cold, yeah.
degrees out Fahrenheit and snowing here in Seattle, which is I'm a skier, so I love that, but can be a little problematic for us all.
Yeah. Do you do they ever have problems sort of with getting, I think in one of the previous presentations you did this, where it could get covered in snow if you do have, especially once you probably just have to have your building maintenance go in there, just brush them off just like any other normal unit?
Yeah, I mean, these are basically, we're putting heat pumps everywhere these days for water heating or for space conditioning. And so our mini split heat pumps, where we have one of those Mitsubishi, LG, Daikin heat pumps on the roof or in a garage, and a split system of ductless fan coil in the apartment space, right? That's going to have about the same maintenance requirements as these heat pump water heating systems. Both those are heat pumps that are extracting heat from the air, or in the space conditioning example, when we're cooling, we're trying to discharge heat to the air. It's fairly common, and so dealing with snow, the typical approach is to elevate the heat pump above the snow level, which they asked for about 46 inches in Seattle for the Sandin product. So that's fairly easy to achieve. And then that fan is operating to blow air away from the unit. And so it's, I haven't really seen examples where it's covered in snow so much that it can't function. Yeah.
Got it. Cool. Thanks. And thanks, Garrett, for that question.
Great. Well, we will move on into the commercial heat pump water heating system components. And I alluded to these earlier when we were comparing that residential integrated heat pump water heater to our Jackson Apartments, very custom engineered, built up heat pump water heating system. But essentially what we have is we have our primary heat pump water heater, and there might be numerous of these. Typically, if there's multiple, they're connected in parallel, like I'm showing here in this conceptual piping diagram. These are taking cold water from the city, heating that water up, and storing it in our primary hot water storage tank. That's our second component here. and we're using that as a battery. When someone uses hot water at the tap, hot water is going out here. That's going to require cold makeup water to come into the tank, which will push out that heated water to those fixtures. And then our control system makes sure that we're turning on that heat pump, excuse me, when we need to always keep hot water at the top of our tank. So we always have water available for those units, those tenants that load. The other, or one of the third component to our commercial heat pump water heating system is the temperature maintenance system. And this will be a little bit new to some of us, but we still have this system in our traditional gas or electric resistance water heating systems. We just have to think about it and design around it with our heat pump water heaters, because there can be some issues with dealing with this temperature maintenance load. Heat pumps are super efficient at taking cold water and making it hot. They are challenged depending on the technology used and the control of that technology to take already heated water from the hot water return system and heat it up again. But we'll get into that a little bit later. So we might have a dedicated temperature maintenance system. And what that means here is the hot water returns from our circulation pump. We're pumping that water slowly through the hot water distribution piping to always keep it at temperature. And that goes into the bottom of our tank. And we might have a dedicated temperature maintenance heat pump that's set up in multipass to reheat that water. And then we also, the last component is a control system. We need some way to control these heat pumps on, and that's typically based on a temperature sensor in the storage tank, or in this example, one in each storage tank. That control system might be integrated to the product, and we'll get into that later today and tomorrow, or it might be standalone like I'm showing here, but the control system is our fourth component and always there in our commercial heat pump water heating systems. So we're going to go through these 4 components one by one and talk a little bit about them and some considerations. We definitely dive way more, or dive deeper into some of the design considerations here in session 2 and the later sessions. But this is a great just overall view of what each component does and some considerations for it. So our primary heat pump water heater, this is our engine. This is really taking that cool water and making it hot. It might be one of these large split system heat pump water heaters in most of our commercial buildings, especially the larger ones when we're talking about buildings, 100 units or more, or large office buildings and so forth. The primary heat pump water heater is moving heat into the water. It's taking heat from the ambient air. When we're talking about an air source heat pump, it's taking heat from the air and moving that heat into water. And it's about 3 times as efficient as any other, or as any system, or one of our other traditional systems that's making heat by essentially burning a flame in our gas water heater example, or burning an electrical element in our electric resistance water heater example. So how the heat pump works is, this is simplified, so not only the engineers in the group can follow along here, but essentially we have our split system heat pump water heater conceptual diagram we drew up on the left-hand side, and our pressure and enthalpy diagram on the right-hand side. And enthalpy, we can think of energy content. The further we are on the right, the more energy is in that refrigerant in this example. And pressure and temperature, we can correlate. The higher the pressure, the higher the temperature of that refrigerant. So the first place I always start at is the evaporator. This is our air to refrigerant heat exchanger. We are typically operating a fan to blow air over our heat exchanger, which has refrigerant in it. That refrigerant is at a very low pressure and therefore low temperature. And it's at a low enthalpy state when it starts. So we can blow heat from our air into that refrigerant through the heat exchanger and get essentially free or low cost heat into our refrigerant. So you can see here that we get about 2 units, I'm calling this, of free energy from the air through our evaporator. But we're still at a low pressure, low temperature. So the next thing is we go through our compressor, and this is going to increase that pressure. It's a pump. It's going to pressurize the refrigerant in the system. So there is where we're really adding most of our energy in. So this is electricity spinning a pump or a compressor to increase the pressure in the system. So that's the energy we're paying. So we got 2 units for free. Now we're paying for 1. But because we paid for that 1 through our compressor, that's going to not only boost the enthalpy, but also the pressure and temperature. So now we're at a much higher temperature right here before we go into our condenser. So on the low pressure side, our refrigerant might have been maybe 20 degrees Fahrenheit. We boosted the pressure. On the high pressure side, it's going to be above 150 degrees Fahrenheit typically. So a much higher temperature there. Now we go through our condenser, which is another heat exchanger. This is a refrigerant to water heat exchanger in our air source heat pump example. And so this is where we're transferring the energy out from the refrigerant into the water. And so we go through that and we pump water through the other side of that heat exchanger and we get hot water out, right? So there, we now got 2 units of energy for free. We paid for 1 and we put 3 into our water. So that's why our heat pump water heating systems are typically 300% efficient, is because we're only paying for that 1 unit of energy. And then the expansion valve is a really key component because this is a cycle. We need to start or we need to end at the same place we started. And so that expansion valve is modulating the pressure on each side so that we return to a low pressure, low temperature in that refrigerant so we can extract heat from that air again. And so this process of moving heat is much, much more efficient than any process of making heat like a gas or electric resistance heater. And it's why heat pumps are so efficient and result in an enormous amount of energy savings, especially when we apply them for our water heating loads. So hopefully that made sense to everyone. There are essentially 2 cycles that process operates in: single pass and multi-pass. These are exactly what they sound like. Probably don't need to explain them, but I will. The single pass is taking water at a given temperature, typically cool city water around 50 to 60 degrees. It's heating that water all the way up to 140 degrees or somewhere around there in a single cycle through the heat pump water heater. Counter to that, there's multi-pass, and that's going to take our cool city water in at 50 or 60. It's going to add 10 degrees and put it out at 60 to 70. Once that water gets up to 110, we're going to put 10 degrees in it still, 120 back into our storage tank. But you'll notice that our connections to the top are on the top of our storage tank in the single pass example, and more mid connection in the multi-pass example, common to a gas water heating system. And that's because at the beginning of this heating cycle, we might be getting 70 degree water in, and with a multi-pass, only heating that up 10 degrees to 80, and then it needs to go around for a second pass. Now 90 to 100, 100 to 110, and so forth. And so if we put that connection at the top of the tank, then there's going to be periods where we're taking in 60, 70 degree water and dumping 80 degree water at the top of our tank, which now we have lukewarm water that's going to flow out first to our occupants and going to be an issue. So it's really important that we understand what heating cycle our heat pump is intended to operate in, whether we can set it up in either configuration or whether a manufacturer is only going to allow us to set it up in a given configuration. Typically, the single pass heating cycle is much more efficient and is used for the primary heating load, taking cool water in from the city and heating up to our usable temperature. Whereas our multi-pass heat pump is less efficient, still fairly efficient, especially compared to a gas water heating system, but it's less efficient than our single pass heating cycle. And this is typically better suited for a temperature maintenance load where the water is going out at 120 degrees to the fixtures, returning at 110 degrees to our central heat plant. And so we want to add about 10 degrees to it, or maybe 20 degrees to it, and that's where a multi-pass heat pump really shines. And so there's definitely some considerations with our heat pump technology. The first is typically we're talking about air source heat pumps, so we need a source of air, and that air needs to have heat in it, or it needs to be a heat source. You can have water source heat pumps, and in that case you need a source of water, of course, with heat. The heating cycle is also a consideration that you need to be aware of, whether it's designed to be a single pass heater or a multi-pass heater, and whether you can change between those in practice. Some manufacturers and technologies allow that. Others, like CO2 systems, are only going to operate in the single pass mode. And that ties back to that refrigerant used in that heating circuit, or that refrigeration circuit, excuse me. The electrical connection, we might be providing, or we might be typically specifying gas water heating systems. The electrical engineers that we're working with might be assuming that early on. So please make sure that you're coordinated with the electrical team early on in the project. And the other thing to consider is some heat pumps will be 3-phase at 208 voltage. Others will be 208 voltage at single phase, and so forth. And so really understand what the electrical requirements for that device are is a critical thing for us all in any system design. The water connections. Is freeze protection required, or do I need it in this system? When we use split system heat pumps, we might locate that compressor, that heat pump, remotely from our storage tanks on our rooftop. And we might want to put heat trace on that piping to ensure that when it's 20 degrees outside and this heat pump's extracting heat from the air, the pipes aren't freezing too. Right? The hot water pipe's going to have heat going into it. The cold water pipe's going to be pulling from the city main, typically around 50 degrees. But as soon as that process stops, there's not going to be heat or flow through that piping anymore, and so there's potential for freezing, and we want to be proactive about that. So understanding where the water connections are they outside, and do I need freeze protection for the environmental conditions I'll see for this given building. Condensate management. Heat pumps make condensate. They're actively taking heat out of the air. The air typically has moisture in it, and that moisture can condense on that cold evaporator coil. That condensing, fluid turns into condensate and drains out. Typically, there's a condensate drain pan on the bottom of these units, and we can connect a pipe to that to take that to an appropriate location. If we put these on a rooftop and it's making condensate, and then that condensate freezes, we're going to create an ice skating rink for the maintenance personnel. And I'm not sure that they're, if that's the best approach, or definitely some consideration that we should be thinking about. And then maintenance and access, we covered this earlier, but there is an evaporator, which typically has a filter on it, and that filter needs to be cleaned on a quarterly basis because there's dust and lint and so forth that's in the air, and that can be drawn to that coil as we're pulling air through that evaporator. There's other maintenance items, but really there's nothing above and beyond what we're typically used to here in our mechanical and plumbing world, right? These are fairly standard maintenance procedures, but they might be different, or like an air filter, we don't have that requirement with a gas water heater. system. So it's just important that we understand that there is that requirement for that personnel to address. And then access to this, if we put these on a penthouse roof that they need a ladder to go up and access, that maintenance procedure probably won't be attended to as frequently as if it was in a much more accessible location. So be conscious about where you put these heat pumps and how you're going to ensure access to them after the project's constructed and the maintenance personnel is doing their routine maintenance procedures. And then the last item on my list is the sound level and noise considerations. Both gas and electric resistance water heaters are fairly quiet, don't really make noise. Here with heat pumps, we have a wide array of noise that we can generate from one product type to another. The small residential systems are very, very quiet. The larger commercial systems can be quite noisy. So just understanding what type of technology you're working with, ask that manufacturer for their sound power levels. But there are compressors and fans that spin, and those typically generate noise. So if we're putting these next to a residential window, it's probably not the best place. If we're putting them on a rooftop, we probably want some type of isolation from that roof, especially if it's a larger commercial piece of equipment that might shake a little bit during normal operation. And then now the next component is our primary storage. This is where we're storing our hot water for use. We can think of this as our battery bank. These tanks are all connected in series, meaning the top is connected to the bottom of each one. And that allows us to really extend our thermal volume, having our cool or bottom tank here and having our hot top tank at the end of that circuit. We can do this with batteries too, is we can either connect them in series or in parallel. There might be certain advantages to connect them one way to the other in a given system type. If you're looking at single pass primary heat pumps, most likely you're going to want to connect them in series. If you're looking at a multi-pass heat pump water heating system, you might want to connect them in parallel, or you likely will. In parallel, you want to make sure your flow is balanced, because now you have 3 flow paths through the tanks. So if one flow path has low pressure drop and another has a high pressure drop, you're going to get a lot of flow through that low pressure drop circuit and very little through the high pressure drop circuit. So equal distance piping is one of the best ways that I've found to essentially balance those tanks and ensure that there will be uniform flow through multiple tanks in parallel. In series, we don't have that balancing requirements, and there's a little bit of a simpler control algorithm too here that we'll cover in later sessions next week. But this can be a really great way to essentially take 3 storage tanks and make them one very tall storage tank. You can think of storage tank 2 on top of 1 and 3 on top of 2. And we're creating a very tall storage tank with a lot of hot water at the top, and that we can pull the cool water all the way down to here to have a little amount of cool water at the bottom there. So definitely one of the considerations for the storage tanks and the heat pump water heaters is how you're connecting those. Other considerations is the physical space, the room and the door sizes. We'll talk about sizing next week, but we can trade off between our heat pump water heat capacity and our storage tank volume. If we provide more storage volume and less heat capacity, we can meet the same load as if we provide a lot of heat capacity and very little storage volume. Typically, it's more economical to provide more storage volume, as heat pump heat capacity is expensive. But if we provide more storage volume, we got to make sure that storage tank is going to fit through that door and is going to fit in that room that the architect laid out for us. So critical. It's an easy one, but make sure you attend to it or consider it. And then vertical is better than horizontal. We're going to talk about stratification, and it's important. Basically, cool water at the bottom, thin transitional layer of warm water, and then a lot of hot water at the top. It's a very good stratification. Vertical tanks are better at achieving that than horizontal tanks. And then one of your considerations, right, is going to be if you have multiple tanks, are they in series or are they in parallel? How does that align with my heat pump water heater? Is it in single pass or is it a multi-pass? Other considerations include the height of the control sensor. This is when we're turning things on. If this is very low in the tank, we're going to turn things on more frequently and have shorter cycles. This is very high in the tank, we're going to turn things on less frequently, but have very long cycles. Typically, we want to be somewhere in the middle or about 30% of the storage volume. So we can imagine that there's 30% below and there's 60% or the remainder above 70%. Piping connections and sizes. If we're doing our tanks in series, the flow is going to go through those series tanks. So we want to make sure that our pipe connections are appropriately sized for that flow rate through the tanks. And then also, where are they in relationship to the top and bottom of the tank? If we're flowing in our top inlet and out our very top outlet, we're only going to use this volume of water, which means we have an unusable volume down there, which we're not actively heating or controlling to. So we're going to reduce the effective volume of our storage tank. So pulling our inlet as far down as possible is the best you can get. Typically, it's not at the very bottom of the tank, but I believe tank manufacturers are looking to design a tank that way specifically for heat pump water heaters. But understanding where those connections are and how they relate back to our multi-pass or single pass heat pump water heaters is one of the key considerations for success. Insulation levels, we might be storing very hot water in our storage tanks with a CO2 heat pump water heater. Typically those are making 150-degree water. So we want to increase the insulation level of our storage tanks to reduce the losses to that room environment or wherever the storage tank is. I would highly encourage targeting R16 top coat insulation. Most manufacturers provide this now. R11 was the old standard, and that's often not as appropriate, not as a very appropriate level of insulation for the hotter storage temperatures. Thermal isolation. When we have a lot of hot water in this tank, the metal of the tank is essentially the same temperature as the water. So if our water is 150 degrees, that metal is often close to that temperature. So if we put this on a concrete pad, we're going to have a lot of heat loss to that concrete pad. So typically we just put an R10 rigid insulation foam under that tank, and that foam, if you get the correct specification, has the appropriate, it can hold this tank full of water, is what I'm trying to say. It's designed appropriately for that load. And then maintenance and access, same maintenance procedures here for these tanks as any other tanks in our water heating systems, but we do need maintenance and access to them to make sure that we can keep them clean and operable for the duration of the system. So we'll pause for questions here. We got about 25 minutes left, and we're going to cover a little bit on temperature maintenance and then a little bit on controls and wrap our session up. So any questions we have out there, Trevor, at this time?
Nothing in the questions tab so far. But yeah, if you have any throughout the remainder, please drop those in there, and then we can address them as they come in.
Great. We'll keep moving along here, and we can answer some at the end. So the temperature maintenance system, the temperature maintenance component to the commercial heat pump water heating system. This is what's keeping the water in the distribution system hot. Typically in our large commercial multifamily buildings or commercial buildings in general, we are using a pump hot water circulation pump to circulate water at a low flow rate through the distribution piping. So the water goes out, is pumped at a low flow rate through each one of these risers and back. So we might have our domestic hot water heating system in the basement. We might have a large 2-inch hot water main going across level 1, and then multiple maybe 1-inch, 3/4-inch risers that go up. They serve a bunch of units, 2 showers in this example. We typically have some way to balance each one of those loops, and then we collect them all at the top and route that back and put a circulation pump on that to draw water through that piping circuit slowly. So all those components are included in that temperature maintenance system. That distribution piping, the mixing valve, the circulation pump, and then we might have a dedicated heat source or storage tank, or both. In our gas or electric resistance system, this is what we typically don't have. That return water is just taken back to our primary storage tanks, and our primary heaters would reheat that water. The Seattle Energy Code specifically calls out single pass heat pump water heaters as the primary heaters. And if you have those, you must have a dedicated temperature maintenance system. And so we're going to go into a lot of detail on designing these systems and solutions for different equipment in next week in session 2, but just an overview here of why it matters. So heat pumps, single pass heat pumps are really efficient in making cold water hot. We can store this water in a storage tank. It's great, easy. Hot water then basically goes out to the distribution network, and often we're putting a mixing valve here because we're storing water at above 120 and we want to send it out at 120. So we're mixing this 150 degree water, 140 degree water with a little bit of cool water from the city, typically at 60 degrees Fahrenheit, and it's going out at 120. Really efficient way for the heat pump to operate in. Now, if we add a hot water circulation pump, we're also going to connect that to the cool side of the mixing valve, and that's typical design if you look at any hot water mixers out there. But that pump's going to continuously or nearly continuously circulate water in the hot water distribution network in a commercial application. So if we take that warm return water, probably around 110 degrees, and put it back into our storage tank, and that's operating continuously, when we don't have a cool water load over a nighttime period, or a hot water load, which is bringing in cool water, then that tank will destratify and mix. So before, we had a very good level of stratification, a high effective storage volume, a lot of hot water to use. Now we bring that back and we essentially mix it, and because it's operating continuously over a few hours, it will mix that tank down, and so now we have a much lower effective storage volume and maybe only a little bit of usable hot water at the top. If the heat pump turns on, it's going to draw in some of that hot or warm 110 degree water, and it might not be reliable or efficient at operating at this point, and it might create an error or an alarm in our system. And why is this happening? Well, the single pass heat pumps are operating in a single pass heating cycle, and the components, the evaporator, the compressor, the condenser, are all sized for a typical range of operation. And when we return warm water back to them, and it's a very cool ambient air condition, that's when we start to run into issues and alarms with these heat pumps. Their components in a single pass heating cycle weren't necessarily sized or designed for that application. We can only do it in a limited amount. And so that's really the issue with our temperature maintenance system, and why at Ecotope we encourage a dedicated temperature maintenance system. We're essentially separating this load from our primary load, as it allows this heat pump to operate in a much more reliable and efficient state, and also takes this control issue out of our hands and eliminates it. So there's two design solutions that we commonly implement, and these are also indicated in the Seattle Energy Code under System Design, which is section C404.2.3.3. And we will cover these in more depth next week, but essentially we have an in-series example, and we call this the swing tank, or an in-parallel example with a multi-pass heat pump water heater. So here we can essentially draw a line down the page and separate that temperature maintenance, hot water circulation task from our primary heaters. And we can do the same in this parallel example. And we'll dive into how these systems work and operate, and why you might choose one or the other for a given building type or a given technology in next week's session. So please join us more for that. But unfortunately, we don't have the time to get into this today.
Yeah, Colin, I know we'll get into that a little more. Just had sort of a quick question, and let me know if this should be saved. But someone had asked, like, in a multi-tank system with an inline series, how can you swap out a tank when it fails?
Yeah, great question. So it's more on storage tank design. Typically when it fails, I don't think I've ever personally run into that, but I would imagine if it failed, the system would need to be shut down, and you'd need to pipe around that tank, or be able to provide a tank in a timely manner, so that you can get that system up and running again. That is one advantage. If you have parallel tanks, you can essentially shut off one of those parallel circuits. Storage tanks, in my opinion, don't fail that often. It's just a metal cylinder, essentially. And so if we're maintaining those tanks, then that's not that great of an issue. But yeah, great question from our audience today. And it would require some field piping around that tank to get that up and running again.
Perfect, thank you.
And our last component is controls. So like I said, we need some way to turn the system on and off. And so we typically have two control options. We either have a third-party controller or we have our internal controls. And so in our internal controls example, the manufacturer will likely provide a control system with their heat pump, and there will likely be a temperature sensor in a split system application that we'll need to put in a storage tank. There might be two temperature sensors, one to turn off and one to turn on the system. Pretty simple, but essentially we're going to set that system up to target a delivery water temperature, and then have a thermal on and off temperature, or thermal on and off engagement based on the temperature sensor in the tank. This is a third-party controller that we have at Jackson Apartments, and we are logging or measuring the system performance here, looking at how efficient the system is as a whole. And so we have flow meters, additional temperature sensors beyond control, and a few other things in this system. And so we utilize a third-party control system that can actually communicate with the heat pump, pull data from that heat pump, and report it to a cloud so that we can access it from our desk and track how the system is operating, and report on that to our utility partners who are working with us in this example. The third-party control also allows us to send out email and maintenance alarms, which can be super helpful, especially to those who are less familiar with the operation of these systems. So there is some great benefit to those third-party controls. The other benefit is that third-party control system can typically control other pieces of the system, not just the heat pump. So if we have any electric resistance backup tanks or circulation pump or other components in that commercial heat pump water heating system, can typically be controlled if you specify the right components by that third-party control system. That's less so the case if you go with the manufacturer's internal controls, but there is some limited capability there depending on what manufacturer you are working with. And so in our Sandin HopeWorks example, we took a sensor that the manufacturer provided and landed it in the storage tank, and that communicates when to turn on and off that heat pump. And then there's another sensor at the heat pump at the cold water connection. So as soon as warm water starts going up this circuit, that's what's turning it off. So we can have a very simple internal control system. All that's coming from the manufacturer, and it's pretty straightforward. In our larger systems, it's going to mimic this. Our larger commercial heat pumps, they're going to provide or have specifications on a certain temperature sensor that would be buried in a tank, and that's going to communicate with the internal controls to turn on and off that system based on domestic water load. And like I said, third party might be, a good idea in some cases. It's definitely going to add cost to the project, so it might not be the best idea in all cases, but it does allow us to look at the system remotely and also communicate with other pieces of equipment in that system. So this is actually a picture of a control system from the Block 11 project, which is Sitka Apartments right by REI in Seattle. And that has a water source heat recovery system where we're actually using the heat from the wastewater in the plumbing system to provide domestic hot water to the building. So there's a sewage vault that we're extracting heat from, which sounds crazy, but it works fairly well. It's definitely more complicated than our air source heat pump systems, but there's a lot of heat in that wastewater, and we can extract that and put it into domestic water for domestic applications at a relatively high efficiency. Now, those two water streams are never touching or even getting close to touching. There's about 3 walls of separation between that wastewater and that potable water. So no concern there, but because we had those additional control components like a sewage pump and backup water heaters and so forth, we decided to implement a third-party control system. Along with, we wanted to track the efficiency of this system and report on it, as well as make sure that maintenance and everything else was being attended to in this example. And so we can pause for questions here before we go into kind of a wrap up on do I have a good candidate for a heat pump water heating system? But any key takeaways here from the group regarding the components, any components that you would like to learn more about in future sessions. I promise you we'll cover more on the temperature maintenance, but happy to take any recommendations or suggestions here, or just hear what your key takeaway was.
Yeah, and I think while we let people get those in there, we did have a question come in. I think it's a really good question and something that I think that we're all sort of thinking about moving towards. But they asked for heat pumps for hot water. Is there any crossover for heating air? And you had mentioned previously, like for using cooling. I think that's sort of like the next logical step. So could you speak a little bit about that, of like using the different applications for both like heating and cooling air?
Yeah, absolutely. So we can integrate our heat pump water heaters with our heat pump space heaters. That's possible. There's numerous design solutions and equipment that you can do that with. If you're looking at a VRF system, a variable refrigerant flow system that one of the big name manufacturers uses, they typically provide a hydro kit, or you can get a hydro kit, which takes that refrigerant and exchanges heat to water. And so now you can use that water heat to put in a storage tank and store it with the domestic application. And so you can definitely combine those two systems together. We are really focused on these presentations on really repeatable systems for the entire industry. And what that looks like is systems that are more plug and play, not tied together with other building systems and really isolated to that domestic hot water task. But Ecodope has had great success doing systems that are tied together, that tie the space heating and cooling requirements with domestic hot water heating requirements. One of my favorite examples is from a casino we did out or a few casinos, but one of them especially out on the Olympic Peninsula, where we have a casino game floor area, which always has a consistent cooling load. Slot machines make a lot of heat. And so we can, and a hotel above it. And so we can take heat from those slot machines and actively cool that game floor and put that heat into hot water for the hotel residents to use. So once again, it's looking at that in a holistic approach of tying those two systems together. Like I mentioned in the restaurant kind of kitchen example of finding sources of waste heat and looking at them as sources of potential water heat. And there's numerous examples of that, whether it's an electrical room or a communications room or a casino game floor or some other area that has a consistent cooling load, because it's really making sure that you match that cooling load with the domestic heating load. They need to be at the same time typically, or you need a large storage tank to buffer between those time of demand. Yeah, excellent.
Awesome. Yeah. Awesome. Thanks, Chris. Thanks, Colin.
So is this project a candidate for a commercial heat pump water heating system? Is it a multifamily building? Then it absolutely is. We can save an enormous amount of energy in residential applications. We use a lot of the energy usage in a residential application is for that domestic water heating, taking showers, cooking, cleaning up after we cook, doing our laundry, and so forth. But there's other facilities that it definitely makes sense to use a heat pump water heater. This is looking at the loads, how much water heat is needed on a given basis across a wide variety of building occupancy types. So senior care facilities, right? Those are of course, along with inpatient hospitals, going to have a high hot water load. So a lot of savings possible there. If we're looking at religious worship where people are only there maybe once a week on a Saturday or Sunday, and they're primarily just washing their hands after using the facility, much lower of a water load. So there's going to be less savings overall. We're going to have a longer payback with that system than we do with some of our residential systems up here. Supermarkets and groceries, also a great one. We can think of those coolers that are all throughout our grocery stores. Another great example of we're actively cooling those, or we are rejecting heat, and we can use that rejected heat for our air source heat pump water heaters to provide hot water, especially where we have, a lot of grocery stores these days have almost like a small restaurant in them, or a buffet bar essentially. So really just understanding how much water people use in a building is going to guide you to whether it makes sense to utilize a heat pump water heater or not. And I would say, all building cases, it definitely does make sense, but we're going to see a much shorter payback in buildings that use more water on an annual basis, of course. So here's our recap as we're wrapping up. 5 minutes left, so a little bit of time for any questions that come in now or later. But why you choose a commercial heat pump water heating system? Energy savings, code compliance, greenhouse gas emissions reduction, and just future-proofing your building. I assume, and I think all of us out there believe that gas won't get cheaper as we go on. But electricity is typically more stable in some regards than some of those extraction fossil gas sources. And then what is a commercial heat pump water heating system? Well, it can look like a lot, or it can look pretty different between one system to another, but essentially it's a system that provides hot water for the tenants, and it typically has 4 components. And those components are a primary heat pump water heater or a primary heater, a primary storage tank or somewhere to store that hot water, a temperature maintenance system, which might be integrated with our primary tanks, or it might be a dedicated temperature maintenance heater and heating system, and then a control system, some way to control those components, whether it just be the heat pumps or multiple accessory components to that domestic hot water system. And then what makes a good candidate? All multifamily buildings are great candidates. Hotel, motel occupancies, also fantastic candidates, but hospitals, senior care facilities, fire stations, other occupancies which typically have high water use or a high hot water load are fantastic candidates for commercial heat pump water heating systems. And then a reminder on our scope and sequence, what we are talking about next. Please join us for session 2, 3, and 4. Session 2, we're going to be talking about more design considerations that are essential for success. We all want to be successful and have a really reliable and efficient system, and so that's what that's targeted at. This is looking at the system more through the designer or engineering lens, whereas today we were kind of in the developer world, but a little bit on the engineering side as well. Session 3 and 4 are hosted by my coworker, Evan Green, who's fantastic and knows a lot about commercial heat pump water heating systems. And he's going to be talking from design to implementation, how to take that design from the engineer and implement it into the building successfully. And then session 4 is all about commissioning and maintaining that heat pump water heating system operation. So I hope you all join us for future sessions, and a huge thanks to Armando and the Lighting Design Lab team, along with Seattle City Light, for hosting us today. Always a pleasure to work with those folks and to be able to share, what we can with you out there working in the industry.
Awesome. Thank you so much, Colin, and for everyone joining us and all the great questions. I feel like they really would spark some good conversation there. So really appreciate everyone joining us. Like Colin said, please join us coming up 1st, 8th, and 15th for part 2, 3, and 4. Just do make sure that you sign up for each one individually because you won't be signing up for all 4 just off the bat. So please go to the Lighting Design Labs and sign up there. I think that's all I have. We don't have any closeouts. Someone did ask about retrofitting. I think we'll get a little bit more into that in previous or in upcoming sessions. So please.
Retrofitting we will definitely dive into. There's a few special considerations there. My number one point when we start talking about retrofitting is you want to accurately size the system for the domestic load that you're going to experience in that building. A lot of these systems out there are way oversized because gas water heating capacity is cheap, and that ensures reliability and redundancy in the system. You can size your heat pump water heating system to that same regard, but it's just going to be more cost effective if you appropriately size and accurately size for the load that is predicted to be for that building type. And we'll get into sizing in session 2 and introduce the EcoSizer, which is a free online tool to help us all size commercial heat pump water heating systems.
Great, yeah. And just Colin has up here the exit survey. So there's just a few questions there about how we did today and some sort of the main things you want to learn for future. So if you still have that slide open, please navigate and drop some responses in there. So I think we'll just leave it open just for a couple minutes, just let people respond. But yeah, with that, I think, and close it out there. But thanks all again.
Thanks, everyone.
Thank you both. It's been a great one. Closing it out.